AP Calculus AB, Unit 6, Day 3. This is a warm-up. So try the problem, pause the video. The more of these you do, the better you're going to get. Okay, so try and draw a picture first, create some variables if you need to, put all the information on the picture, come up with a relationship. Identify the rates, which might be tied to the variables you choose. What are they derivatives of? Are they positive or negative? How do you connect the rates that you know with the rate you need, but without the rates first, just first an equation that relates the variables, and then take the derivative implicitly and plug in the values you know to find the thing you need. So go ahead, try it, pause your video, try the problem. Okay, assuming that you guys have tried this, let's see, a road and railroad cross at right angles. So, you might draw sort of a, looking down on it kind of version. A car is going, so one of these is the road. I mean, this could be your road. This could be the railroad. So it might be good to just label those, keep those straight because they look the same. A car going 60 miles an hour crosses the track. So car, you could draw the car going up or down. That really doesn't matter. You could label it. I'm saying it's already gone through the intersection. So if we drew down here, I'd probably draw it down. It's going 60 miles an hour. So put that on there. 10 minutes before. So 10 minutes before a high-speed train traveling at 90 miles an hour. So it goes through the intersection before the train does. Now the train, how fast is the distance between them changing 10 minutes after the train crosses the intersection? So the train's already gone through it. And it's going 90 miles an hour. And this is going to be 10 minutes after is what we're thinking. Okay, how fast is distance between them changing? The distance between them would be the length of this direct line. So we're trying to find the rate change of that line. Now, we probably need to create some variables. So I think this is going to involve a right triangle. So I might just use some typical variables for right triangles, A, B, and C. And so we are looking for dc dt. Do you think it's positive or negative? Are they getting further apart or closer at that point where you're being asked? Further apart should come out positive. Now this rate right here, since I put a B here, this is tied to dB dt, and it is positive because B is getting longer. This rate right here is tied to that, so this is dA dt, and it is also positive because A is getting longer at this point. So we have a lot of information, on this picture. We're looking for dc dt. Now the time stuff, if this is 10 minutes after this, that means that this represents 10 minutes of time has passed. But this one's going to be 20 minutes because this one said that the car passed through the intersection 10 minutes before the train. And now we're looking at 10 minutes after the train has gone through, so that'd be 20 minutes after the car has gone through. I don't know if that makes sense. So we're probably, so what's the relationship between these? So we have a nice picture. We've kind of identified everything. What's the relationship that ties dA dt, dB dt, and dC dt? Well, what's the relationship that ties A, B, and C? Diagram theorem, A squared plus B squared equals C squared, right? Now, are any of these values constant, A, B, or C? Because if they are, we should plug them in now, because that just makes work a lot easier. Not that you have to, but they're all changing, so we can't plug any of them now. So we're going to take the derivative 2a to the first power, dA dt, plus 2b dB dt equals 2c dC dt. So that's your derivative. And this is what we want, right? We have dA dt and dB dt. Now we don't have A and B. That's not 10 and 20, and we don't have C. This is time. These are the actual lengths. So we have to use the relationship that you guys have. So this was the relationship. But there's this formula you guys learned back in like algebra or something. D equals RT. distance equals rate times time. So we need to use that. So now you got to be careful because, so for this one right here, that's going to be 10 minutes times 90 miles per hour. The problem is the minutes and hours aren't the same kind of time units to cancel out. So we gotta change the hours to minutes. So there's we need to do a conversion here. There's 60 minutes in an hour. So then that would give it to you 90 miles per 60 minutes. Now the minutes cancel, and we get 90 over 6 is 15. So 15 miles is what B is. But you can't plug that in before you take a derivative because it's changing. Over here, A, similar idea, 20 minutes times 60 miles per hour, but we got to change it to miles per minute. So 60 minutes in an hour. Now, that you should do it in a way that the variables end up canceling out. That's how you know you did it right. So that's going to be 20 miles is your A value. So now we have the A and B, but we do need C still. So we got to go back to that original relationship, A squared plus B squared equals C squared, to find the C value. So doing a little more work. 400. Was at 225. 15 squared. If you have to, can you pull off a little work on the side? 5 times 5 is 25. Carry the 2. 7, 0, 5, 1, 5, 12. 225. So that's 625. And then you got to take a square root of both sides, plus or minus. Now, I think that's a perfect square, but I could always break it down. And there's 425, so that's 24. That's 20. It's 25 times 25. Perfect. So C is 25 at the moment we're being asked. It's changing. So now we have all these values, and we can plug them back into here. So 2 times A was 20. dA dt was positive 60. Again, I'm always super sensitive about positives and negatives for the rates because it's so easy to mess up. B was 15, and dB dt was positive 90, and C was 25, and dC dt is what we're looking for. So we're almost done. Now we just got to clean this up. So 2 times 6 is 12, 24 with 2 zeros on it, right? 30, 27 with 2 zeros on it. So that's going to be what? 5,100 divided by 50. And so dC dt equals 102. And what are the units? Well, C should be miles and time should be hours. So it's miles per hour. And it came out positive like we thought it should. Okay. Now, on tonight's homework, so that's it for today. Tonight's homework is this worksheet number 3, AP Classics Related Rates. And it's 4 problems, but they're definitely challenging. So I was going to try and give you guys a little bit of a heads up of some tips and stuff. Now, the first one's pretty simple. Circle inscribed in square, showing figure where the circumference of the circle is increasing. So they're giving you dC dt. As the circle expands, the square maintains tangency. So the square is getting bigger, the circle is getting bigger. Find the rate at which the perimeter of the square is increasing. So you got to come up with an expression for the perimeter. Perimeter equals 4s. And then take the derivative. Now you're going to get a ds dt. Now the thing you need to realize is that you have a radius, right? And then you have the sides of the square, but the sides of the square are 2r, right? So r is the distance. So that's from, this one's a little tough because from the circumference, 2 pi r, you could write You could do dCdt. And they gave you dCdt, right? From that, you can get drdt. Okay, from drdt, you can get dsdt, because if s equals 2r, then dsdt equals 2 drdt. So once you have drdt, you can get dsdt, and you're going to need that for your perimeter. And then at the instance when the area, find the rate of increase in the area enclosed between the circle and the square. So that's this right here. So you need to come up with an expression for that area first. Simple geometry strategy. A shape minus an inner shape gives you a shape in that area in between. Take derivative of it implicitly. Probably got to use your drdt and your dsdt or something to help you on that one. Number two, we call this like the balloon animal example or something. Right? You got, twist balloons into shape. I don't know. You might think it's like one of those long, slender balloons, but here's the deal. It says shape of cylinder with hemispherical ends of the same radius as that of the cylinder. The balloon is being inflated. That's dVdt, centimeters, cubic centimeters per minute. At the instance radius of the cylinder is 3 centimeters. The volume of the balloon is 144 pi cubic centimeters, and the radius of the cylinder is increasing. So giving a bunch of different rates. At this instance, what's the height of the cylinder? So I think we need an expression for the volume of the whole thing, which is the volume of a cylinder plus the volume of a sphere, right? Because there's two half spheres, so that makes a whole sphere. So the cylinder is pi r squared h, and the sphere is going to be 4/3 pi r cubed, if I memorize that correctly. So anyways, you're going to use this. Part A isn't calculus yet, it's just some geometry. You're going to try and solve for an h. Part B, at the instance, how fast is the height of the cylinder increasing? So it says at the instance, the radius of the cylinder is 3, the volume is 144 pi. So you can use that to figure out what h is at that moment. Okay? And then you're going to try and find dh dt. So you're going to need dr dt also, and dv dt. You have dv dt. We gave that to you. And they give you, I think they also gave you drdt. It says the radius of the cylinder is increasing at a rate of 2 centimeters. So you have drdt too. So this next one's a little crazy, the trough. So, you want to create some variables, right? It says trough in the figure shown is 5 feet long, always 5 feet long, right? It has a vertical cross sections of inverted isosceles triangles. Okay, upside down isosceles triangles, 2 equal sides with a base of 2 and a height of 3. Now, okay, at any time, let T and H be the depth. So H is the depth of the water, or the height of the water. Find the volume of water when the trough is full. Okay, so you got to come up with the volume relationship for this. So this is like a prism on its side with triangular bases. So the way you find volume of a prism is the base times the height, the base area. Now the bases are triangles, so that's going to be 1/2 base times height just for the triangles, and then you have this other height, which is a different height. Now this is the height between, for the prism. Anything that's not changing, plug in. Okay, are any of these dimensions not changing? The base right here is changing for these little triangles in here. The height of the little triangle is changing. This height of the prism is constant. So just plug a 5 in right now. That's going to make your life a lot easier. And these two h's aren't even the same h anyways. Okay, so it's a little similar. Now, let's see. I think you probably want to try and use the strategy we use for cones and get the variables all one variable. It says, what is the rate of change of H when the trough is quarter full by volume? I think we did a problem kind of like this with the cone. It was like quarter full by so we're looking for dH/dt on part B. So you probably would like to get this as all H's for part B. Okay, and so then you see, well, how is B and H related? Well, just like cones, you guys see the similar triangles? Similar triangles, B over H equals 2 over 3. So the relationship of this over this should be the same as this over this. They're similar triangles. So now you can get B in terms of H, get it in terms of all H. Okay. By the way, these problems should take about 10 to 15 minutes each when you're kind of doing good. Now, the problem in the back is really crazy. Tightrope walker. These are actually all problems that were on old AP exams. So this one, this one's kind of crazy. It says a tightrope is stretched 30 feet above the ground. Okay, this is the tightrope right here. Between the J&T buildings, which are 50 feet apart, which isn't on the picture. So we should probably add that, right? And they're always 50, so I think that's never changing. This tightrope is always 30. This is always 70. Tightrope walker walking at a constant rate of 2 feet per second from point A to point B. So the tightrope walker right here, very simple, is moving in this direction, right, from A to B, and they give you a rate that you probably put on there. I mean, we can just do it right now, 2 feet per second. And it says is illuminated, the tightrope walker with a spotlight 70 feet above point A, as shown in the diagram. So there's a light up here. So this is one of those shadow problems that you guys should love. How fast is the shadow of the tightrope walker's feet moving on the ground when she's midway between buildings? Is it moving at 2 feet per second also? So here's the shadow of the tightrope walker. Okay, and so we're looking at how fast is the feet move? How fast is the shadow of her feet moving? So this is what we're looking for. And it says when she's midway, so that'll probably be exactly halfway between the buildings, 25 feet from each one. Now we got to create some variables here for these that tie these rates. Now we're looking for some relationships also. I see some right triangles being formed here that are also similar triangles. So it's either Pythagorean theorem or similar triangles. But we probably want to create a variable for this chunk right here to assign this rate to. You could do it over here to this chunk, but it just makes more sense here. So I'm going to call this x. So this is dx dt. Is it positive or negative? Positive, because x is increasing. If I tied it to this length instead, it would be negative. So we got to create a variable down here because that's the rate we're looking for. So I'm going to call this y. I'm going to call this dy dt, and it's positive. So that's what I'm looking for. I'm looking for dy dt. So I got to figure out, well, how do I relate x and y together first, similar triangles, and then take the derivative implicitly, use the dx dt they give you, and use any values that you need to. So anyways, that's a lot of help right now. So try these problems, and we will go over them more in the future. But you got to try these. I mean, imagine getting a test with a new related rates problem on it. If you haven't been trying these yourself for sure and just waiting to copy down what I write down, you are not going to be ready to deal with one on your own. So force yourself to deal with these. Even if you get stuck, just try and get as far as you can. There's a bunch of them, and then I'll give you some more help.